All right. So our next topic, class 5, is really the introduction, and it's the beginning of the main journey that we'll have in this class. At least this and the next week will be devoted to machine learning as such, because so far we did a lot of data processing, representation of audio, signal processing, which is required, but we still didn't build any model, any statistical model. We spoke about the importance of doing statistical models and the idea that musicians might use generative mechanisms or generative systems to create music. But even there, most of the statistics was kind of throwing random dice and looking up something which was manually pre-composed. But it's already like a beginning of the concept that you can use some way of shaping randomness to eventually create contents that are meaningful and musically meaningful. You wouldn't probably do the same thing so much in text, although people do that. Kind of there were these, especially in the arts, kind of a dada or these babbling experimental text writing that people would run and write nonsense poems with some kind of automated text reading. You could create using some kind of more designed methods text also by throwing dice. But really the revolution started when you could actually model meaningful things by assessing the probability of these things. So my approach, or an approach that I find kind of interesting also conceptually, shaping this idea of randomness turned into structure, is using information theory. Again, information theory is not really the regular thing you would look into as a first thing to talk about machine learning as such. But so it happened that my work, at least in machine learning in music, started from this information theory perspective. So let me introduce the concepts. Information theory classes are also usually taught in electrical engineering as such, because it originated as something more related to transmission over noisy channels, error correction. But even today in deep neural networks and statistics, information theory captures significant part because it allows us to think about machine learning in slightly different ways. So let me kind of introduce the concepts of information theory. So the underlying concept about what is information is the idea of an information source. And information source is really a probability distribution over the space of possible messages. So we still maintain here the idea that there are messages that you're passing some kind of either symbolic or continuous signal as well. But the variety of these messages is limited in the sense that they have some kind of a structure, but it's probabilistic. So if you know the probability distribution, this becomes your information source. Now, once you have this source and you have these messages that the source spits out, so you have some kind of a random number generator, you bang it, you get a message now. You could now have several tasks at hand. One could be how we can encode them more efficiently. Another one, if you have an encoding of these messages, you want to transmit them to somebody else, and the channel might be noisy. So these codes are transmitted and need to be corrected. So there is this whole theory of error correction that might be added to the message, like all kinds of Huffman codes, error correction codes that will actually either detect and hopefully correct, or at least send you some kind of a notification of that you need to resend the message. Talking about audio video is that okay, the internet is unstable even here. You might be willing to compromise on the original quality of your picture or your sound recording or music recording to get a lower rate. You basically compress for the purpose of either storage or transmission. So you can encode a message more efficiently if you're willing to compromise the quality. So this is kind of an overall setting of information theory. Really, one thing to notice, there is no classification task here. There is no really decision making, although the same techniques of clustering might be used as well for creating the codes, but the whole setup is slightly different. I'll be mostly talking about the idea that information source is a probability distribution. So if you have a way to encode it, you can then send these messages in a certain way that emulate the information source. So this will be our task, actually. How do we learn the information source? Just to repeat the same idea, the basic modeling or the problem setting is you have an information source as a probability over some domain X. You have an encoding of this domain that will take into account the probability for every message. So X is basically a message that is encoded, it being transmitted, and the transmission is considered as also probability. It's actually conditional probability because there is some noise or some disturbance that will make the signal that arrive change from X to Y. So you send X, you receive Y, and there is a certain probability of seeing Y given X. So the whole effect of this noise channel is basically conditional probability over the messages that you see given the messages that are being sent. This is kind of the problem setting. And then once you have this Y, you might ask all kinds of questions like, well, what is my cost or what is my quality criteria for enduring Y while ideally I would get X. So there is some kind of a cost of this communication error. And given this setting, this is kind of defines information theory as basically a field of study. Now, Claude Shannon, who is basically the father of information theory with Weaver, who was his advisor, and came up with these three postulates or theorems. And I will mention them because once you study information theory, you usually study these three subjects. But we will cover only theorem 1 and theorem 3. So what are these three theorems? One is that information source or messages from information source can be encoded at a rate, and rate means really bits per message, okay, or bits per signal, a symbol in the message, encoded at a rate as low as entropy. So there is a lower bound to the number of bits that you can assign to your messages, and this lower bound can be calculated if you know what is the probability of the information source. You actually have this function called entropy. Entropy, we'll talk about this in a second, but it takes a probability distribution, gives you a number. Okay, so here's the magic. For any information source, you can calculate this entropy, which will provide you a number that will tell you what is the lowest rate at which you can send messages. And why this is useful or interesting, because it gives you kind of theoretical targets or challenges, or sets you the goal of how low you can do. I mean, in this case, this is so-called lossless compression, because the idea is that we actually do not create any distortion. We just encode more efficiently the sequences by taking into account the probability of these sequences. And we will be talking about lossless compression as a concept that will allow us also to generate new music. The second one, which we will not deal with, but I want to kind of mention this for completeness, is so-called the channel capacity theorem, which deals with error correction. And the idea is that if you want to ensure that you correct the error, so the error-free transmission is possible by adding some extra code, which of course increases the rate. Your payload becomes longer. Okay, so you have the bits of the message, and then you have extra bits for the error correction code. But the way it was proved really kind of conceptually as just a rate. So you lower the rate by adding something, and given a channel, which is also probability distribution, you can calculate another number, which is called the channel capacity. And you know how many error correction codes, given that you know what your source is, you can add to ensure that you have perfect or error-free transmission. So this sets a challenge for anybody who's designing error correction codes to see if, at least for some theoretical information sources, where you know what is the entropy and you simulate the channel, you know what is your target. I mean, can you actually find an error correction code that satisfies this limit? Often you will exceed. You'll have a rate which is much slower than this channel capacity, but this is kind of also incredible result that tells you that there is this number. If you know your source, you know your channel, you know in theory that there exists a code that if you add that code, you will correct this at that rate level. So having said that, we can a little bit ignore or forget this for a moment, and we'll move to the third one, which is the idea that I mentioned when I said that information theory deals also with lossy compression, or taking an image and turning this into a JPEG or PNG, or audio, representing this as MP3. But also if you want to extract features and then you want to kind of be able to reconstruct the message from features, which will be something that we do if we think about even kind of like in text and text to message. You can say that text is really low quality encoding. So if you're willing to represent your message with a lot of errors, you have so-called the rate distortion limit. Okay, and this is slightly more conceptually tricky idea, but in the overall, it says that if you are willing to set up your distortion, so RD means rate distortion. If you're willing to set the quality, which means I'm willing to endure signals that are different or have a distortion relative to the ideal or original source signal up to a certain limit, then there is a function that you can calculate that will tell you what is the encoding rate, or what is the most compact encoding that will allow me to send messages which are lower quality, but the quality will not be worse than some limit D that I set up. There's also the opposite, distortion rate. So if you want to set a limit on the rate, which means how much you compress a signal, there should be code that will use this compression that will not exceed a certain distortion. So given a distortion, there is a certain rate, and you should be able to find a code which is as compact as that rate. So it kind of sets you basically this framework, these limits. And a lot of information theory is basically limits on probabilities. So we'll use lossy compression because once we start talking about taking an audio signal and symbolizing this, or kind of having some representation that eventually will regenerate signals which are slightly different, these aspects will come in. Okay, so definitions of entropy. For those who have already seen that, maybe in statistics classes, maybe in physics, because this is the same expression that entropy in thermodynamics has. This is the expression of entropy. Okay, I'll motivate this in a second. We won't have too much time to kind of like go really in depth, but entropy is used all over deep neural networks, right? We actually have entropy, we have cross entropy, conditional entropy. So what this means, basically it tells us that, given a probability P of X, okay, we calculate basically the average, because this is a mean, right? So we sum with the weight Px. So this is the mean of log of Px, or with the minus, it's a mean of a log of 1 over P. So couple of comments which I think are important here. I didn't put them in writing, so I hope you can still capture them from my explanation. One thing is This is so-called a functional. What means a functional? It means it takes a function, okay, and returns a number. Okay, this one is a function over discrete values. If x was continuous, that would be an integral. It'd be slightly more tricky. So just keep in mind that this continuous entropy has a little more peculiar properties than this discrete entropy or entropy over discrete set of outcomes. But if you think about p of x as some kind of a function over the domain x, you plug this into this equation, and from this function you get a number. Okay. So this is one important thing. It kind of summarizes something about your whole probability distribution into a value, and this value has a meaning, as we said. We'll not really prove any of the Shannon theorems, but we'll kind of keep them in mind. Now, what another interpretation here is, actually what Shannon did was he interprets this log of 1 over px, because I include the minus here, so it's log of 1 minus px. He started with the idea that this is actually your coding length. I know that we're not really showing why it is, but kind of think that, log, and normally this will be log of 2, is the number of bits, and the number of bits that you will assign to a message is inversely proportional to the probability of that message. Okay, so if this becomes your coding length, this is the mean coding length over all possible messages from your information source. Okay, so average over your code length is hx, and actually what he proved is that other codes will be longer than this expression. So this becomes the lower limit on the coding length. So kind of with more of a hand waving, I kind of proved the first theorem. That other codes than this log px will have will be, or I didn't prove, but I kind of like stated this theorem in a more quantifiable way, that other codes than log px or log of 1 over px will have longer length than this expression, where we can actually assign that number of bits per symbol. Now these are definitions. I just will keep them as is, just so you know what they are. I might mention them later on. The conditional entropy, okay, this is an entropy of x given some other variable y. This is how it's defined. One thing to take note is that here is the conditional probability, here is the joint probability. You can also think about this as p of x given y times py if you put a base here. So it's like this expression, but it's also averaged on all possible y's. Okay. Now the thing about these quantities, if you think about them as some sort of a number that summarizes how uncertain or how random the source x is, you can show that this is kind of what remains of the randomness if there is another variable y that is correlated in some way or has a joint probability with x. And if you look at the difference between them, this is what's so-called mutual information. And mutual information is a really powerful concept. In some sense, this is where really information comes in. Information is not entropy. Okay, information is really a relative measure between two variables. Information is basically if x is the source and y is what you receive. This is how much information is passed, because if you know something about y, you have some uncertainty about y, the fact that you send a message, it reduces the uncertainty about y, and the information that is transmitted is just a relative reduction of that uncertainty. It's kind of a tricky concept, but I'll just say it again. Information is really a measure between two distributions, and it shows how much an uncertainty about one variable is carried by knowing another variable, and this is symmetric. So just keep this definition in mind. This is the first theorem. This is the first theorem. We said the coding length is greater than entropy, and you can also upper limit this by 1 bit. Relative entropy, KL distance, Kullback-Leibler distance, is used a lot in machine learning, because if you want to compare now two distributions, you have some sort of metric. It's not symmetric, so it's not exactly a metrical thing. But you can notice that if Q equals P, this is 0. You can prove that this is positive. This is a measure for comparing two distributions, how different they are. And the last thing, which is this data processing inequality. So these are all properties which are important kind of to keep in mind, and I think we can kind of understand them a little bit as, I would say as a given, because the nice thing, you can actually prove them. But I think they're kind of intuitively making sense. So what the data processing inequality tells you is that if you have a source X that is then sent over some random channel, if you want, or there's something that happens here that generates Y, and then this Y generates Z, okay? You can actually define these conditional distributions. The data processing inequality is an important concept because it actually tells you that every time you move one step in this chain, you lose information. So the information with X and Y is always bigger than the information from X to Z. Okay, given that, let me just a little bit emphasize or give a little bit more of an intuition about what is entropy. And the simplest idea is really to think about a binary source. In this case, you can think about like flipping a coin, but the coin would be a biased coin. So a fair coin will have P equals 0.5, so you have an equal probability of heads and tails. But let's say you have a biased coin, okay? So here we have head and tails. So a fair coin will have probability half and half. Of course, because it's a binary variable. Yes, question? All right, I'll move on. So because it's a binary variable, you will have 1 bit to represent this. So we'll need, for head, you need 1 bit. For tails, you need 1 bit. This is the probability. 1 over P is 2, right? It's 1 over 1/2. Log 2 shows us that this is 1 bit, and the entropy is 1/2. So on this graph, if we take a fair coin, we'll see the entropy at this value, and you can plug this into this equation, okay? And you will see that, given here 1/2, and this is log of 2, you actually get a 1 here. Now, if we start having a biased coin, let's say a coin that has a probability of heads 0.9 and tails 0.1, we still, in theory, if we just want to encode one symbol every time, we still need 1 bit, right? Because how would you transmit the outcome? Well, you have 1 bit representation. The probability, although, of these events becomes very different. The probability of 0 becomes, or 1 over the probability is 1.11, and the probability of 1 becomes 10. So if we plug this into the equation of the entropy, just calculating these values, we get an expected entropy of 0.467. Okay, so depending which is the tail, which is the head, but if we move to, let's say, if this is the heads, right, 1, heads is 0. So if we move here, right, so we have a 0.9 probability of heads, you will be hitting here entropy of 0.467, okay, on the graph it shows here. So this is an example of this kind of entropy functional, which takes, it's not, it takes a vector of probabilities, not a continuous function, but you plug this into this equation and it gives you a number. And so why this number is meaningful? I mean, how you can actually encode if you know that the coin is biased and you don't want to spend 1 bit on every outcome. Well, so the idea is that, and this is kind of the basis of the compression idea, is so-called asymptotic equipartition property. If you look up in a good book on information theory like Thomas and Cover, information theory, jumping to that chapter kind of gives you the essence of why the information theory works. So the idea is, instead of encoding every event individually, we take a very long sequence, okay? And this will be called eventually a typical set. What is a typical set? It will show that if you look at very long occurrences, you basically sample your information source for a long time, you'll have suddenly this sort of like a partition of all possible outcomes of length n, as n goes to infinity, into two sets: events that practically will not occur and events that will occur. And the interesting thing is that it will occur pretty much in equal probability. So you will have basically messages. So let's say we go back to the example of 0.9 and 0.1 for the biased coin. You will have long messages that have approximately 90%. I just don't want to mix the terms. Yeah, here the head were 90% more probable. So you will have messages or sequences of coin flips where you have 90% of heads and only 10% of tail. So suddenly, if you're willing to go with your n to very large numbers, you'll get only one set of events that is probable, which is all messages that have 90% heads and 10% tails, while messages that have a very different distribution will eventually be very improbable, or the probability of messages here. So each message here, each point here is basically a very long trial of flipping coins. But any trial that actually deviates a lot from this 90% to 10% ratio will be very unlikely. So as n goes to infinity, the probability of the typical set will grow to 1. And the size of the typical set, basically the number of messages, of course, it depends on the lengths of the messages, and it grows like 2 to the power of entropy. Take your time kind of to see that you figure out what it is, but this is kind of the essence of Shannon's ingenuity about information theory, is that if you look at long enough messages, if you do block encoding, you are able to throw away a lot of messages, a lot of sequences that that information source is very unlikely to produce. So, just another demonstration of the concept of rate distortion, and I think it's my last slide for this set of this topic. Just to understand what is rate distortion. So rate distortion is actually the same thing as the encoding, but now we allow to have an error. Okay. So we said that rate distortion also gives you some kind of theoretical bound. This is something that this red curve can be theoretically calculated if we know our information source. Okay. Again, rate distortion doesn't depend on transmission. It's just the idea of loss encoding. So what is the problem we're trying to demonstrate here? We are band limited, or in the sense that we have less bits that ideally needed. If this term is kind of foreign to you, just think about just limiting the number of bits. Okay, it's bit limited rather than band limited. So we have a dice. Our dice has 6 outcomes, and we decide that we are willing to encode this in ways that allow some error. Now, of course, it depends on how you define your error. Here we would say we have a correct transmission if y equals x, and we have just an index of flag that there was error otherwise. Okay, and now let's see how, basically what is the probability of error depending on how many bits we allocate. So if you think that we can allocate, everything for each one of these 6 events, and bear with me that, if you think about encoding, you could, with the previous result of very long codes, you could encode outcomes of a dice at log 26 bits. Okay, so this is kind of a fractional bit, but let's get accustomed to the idea that once we talk about encodings, this could be fractions of bits. So this is the many bits per event that you could encode. Okay, 6 is the size of the alphabet. Log 2 is basically because we're encoding this in a binary way. So if we take this number is 2.5 something or 6, you can check this just by computing with this number. But here is the full bitrate required, and you have 0 distortion. Okay, But let's say we want to go and encode only with 2 bits. So 2 bits means we want to transmit only 4 possibilities, okay? But we have 6 outcomes. So then the question is, how do you partition the 6 outcomes, taking into account the fact that they're equally probable, but then when you think about sequences, if you have 4 outcomes, how you would combine different types of events so that the probability of your error will be minimal, okay? And there is this theoretical result that will show you that at this bit rate, you have this distortion, okay? Or you can go the other way around. If you're willing to have a distortion of 0.2, the probability of 20% of getting a wrong understanding of the outcome, if we're willing to endure 20% error in somebody telling you, something, in a limited set of outcomes, and you will be 80% correct and 20% wrong, you only need 1 point something for, I don't know where exactly this falls on the graph, but you need less bits, okay, and so on. So if you want to encode only with 1 bit, okay, you will fall actually, so you can decide, maybe you divide this into evens and odds or some other ingenious method. I mean, the question is here, can you come up with such a method of encoding? But it gives you this theoretical proof that if you want to encode these outcomes with 1 bit, you can find an encoding that will be, let's say here, let's guess that this is about 0.3, you'll be having an error of approximately 30%, okay? And of course, if we don't encode anything, okay, we'll get at 0 rate, we get this distortion of 0.8, which will be basically calculated by saying, well, I can randomly guess an outcome, and what is the probability that my random guess of an outcome will correspond to one of these 6 possibilities. Okay, so if you calculate the error of just randomly guessing something without having any information transmitted to you about the outcome, what will be your error? Okay, so this is kind of the notion of rate distortion. Yeah, I'll stop here, take some questions. I mean, there's a lot of conceptual stuff here that takes a while to digest, but the main notions of entropy and mutual information, I would like you kind of to retain. Okay.